Welcome back. Now, I want to take you through a virtual molecular dynamics experiment on diffusion and viscosity. We will take a particle and run it through a gas system and see how it moves through it, so that you can see the viscous effects and the diffusion of that particle through the system. And that shows you that in molecular dynamics simulation, you can indeed create a physical situation which applies to the diffusion and viscosity. So, let us turn to our tool here, VMDL, and this VMDL simulation is called Viscosity 1, which you can also look at your own and understand it better. So, let me bring this up and also give you some magnification here. All right. So, in this case you can see that number of green atoms here is 19, and you have number of blue atoms which is representing the gas phase as 181. So, you have a blob of a particle which is moving through this liquid or gas phase, and it depends on what temperature you are in, and looking at how initially in the liquid phase is very small temperature, close to few degrees of 12 degrees of Kelvins, how we can move with this 200 particle system, out of which 19 are different weight, and there is a particle mass is also there, temperature is there is a heat bath. So, of course, we are using canonical ensemble. Here are the properties. Let us show the averages, and also we will look at show some additional properties that we want to control. So, let us start with that. I think the additional properties are somewhere in the back, but let us begin first. So, let us equilibrate the system, and what you are observing here is that this the motion of this particular blob through the liquid system, which is almost very dynamic, and how the diffusion is taking place through the system. So, now if we restart this system again with different situations, so we are going to reset the experiment. Let us look at some of the parameters that we can change. So, let us first change the mass. So, we are becoming heavier, and then again in this case you do have to look at other parameters like gravity. So, let me just find that. Yeah, here are the additional properties. Let us bring them close to us. So, now in this case the gravity is a certain element. So, first we will change the mass, and because gravitational force is constant, I want you to pay attention to that and see what happens due to gravity. So, if you look at now, we increase the mass and the particles have the same gravitational force. So, it will take same time. However, what you are also observing that the particles which are the gas particles, because we change their mass, and this is particle B. So, we are changed the mass of the particle B, which was the liquid side of it. So, because of now greater mass, it has come down, and now you can see the diffusion becomes very difficult, primarily because the mass of the substance through which the lighter particle are trying to diffuse is crowded by the heavy particles. So, we can do that. Now, let us reset this experiment again, and let us see if we can keep the particle mass same, however increase the gravitational force. And this is rigid container and reflecting wall situation. So, we are going to do that. Now, you can see here the concentration, how the concentration is going down, and what is happening with the energy. Now, you are looking at the energy versus time. So, it came down faster because of gravitational forces were different and higher level. Let us pause there, and then we are going to look at the diffusion again, reset the experiment. And by measuring the time it takes for this blob to come down using through this other medium, you can then calculate diffusion constant, because you know the distance and you can plot the properties of diffusion over time period. So, this is where mean square displacement of these particles through this medium, if you then use the Green-Kubo formulation of the velocity of these particles through this medium, velocity autocorrelation will give you the diffusion constant. That is the whole point of doing this experiment, that you are able to calculate diffusion constant. So, now let us look at kinetic energy versus time and start this system again. So, now you have several kinetic energies. So, let me pause it. So, this is for the green kinetic energy. Now, you are looking at the blue particles. So, let us do again. So, you can see the fluctuation of the green particle as it interacts with the blue particles in the gaseous phase where it is going through, moving through. So, now you are looking at the diffusion under that. So, I am going to now do one more parameter by resetting the experiment. I am going to change the temperature to higher temperature. So, once I heat the system, I want to see what happens to the diffusion of a particular species which may have different mass. So, is there a mixing because of the temperature, and how does diffusion and mixing then works into the process. So, you can see immediately the particles, the green particles are essentially diffused completely, they are broken off because of the thermal energy given to them, and they are essentially, instead of diffusing through it, they are mixing. So, now we are looking at different phenomena, but each particle is now diffusing differently, not as a one single blob, but now these particles have a diffusion constant. So, if you look at the velocity autocorrelation for all these particles, and then you can calculate using Green-Kubo formulation, then you will know the diffusion of these particles through the gas phase. So, that really gives you good understanding of the diffusion here, and let us reset the experiment. Now, let us look at the effect of the boundary conditions. So, let us say we say no walls. So, now we created periodic boundary condition, rigid container. First do the rigid container situation. So, in that case the volume is constant, and then we will do piston where the volume will not be constant. So, in this case let us move it. Now, it is periodic boundary condition. So, there is some relaxation from the wall, because wall was hitting and reflecting some of the kinetic energy. So, now in this case there is a relaxation of the gas particles, and now you can see in this case it is now defining a bulk behavior. So, the difference between reflecting wall condition and the periodic boundary condition is that in reflecting wall you are looking at a tube, and the diffusion is through the tube, and so there is a confinement effect because of the walls. In this case it is a very small cube, but now you can see when we have periodic boundary condition, because of the confinement, the particle which was going through, the blob of particle which was going through the gas medium was going straight, because it was confinement effect. But now in this case you can see it is drifting, because if you look at now in a bulk system, the blob can move all over different places. So, there is no confinement effect, and that is what is different. When you look at the two phase flows, and in this case these are the two phases, the confinement effect is very important, and that defines how the diffusion will take place. So, the diffusion will be affected by the confinement effects as well. So, what we are looking at the velocity autocorrelation and how does that change if there is a two phase flow and things like that. So, let me stop here, and I will do one more experiment before we stop this understanding. Let us put in our piston. We are keeping the gravity thing same, but now we are adding the piston on top, and so that volume can change. So, now if you have this situation, let me also look at the volume here. So, volume is constant in this case, but container is with the piston, and so now you are seeing the diffusion in this situation, where again these are reflecting walls, and we have allowed volume to, and you can see immediately the diffusion has become very slow. So, the diffusion has changed because of the Western condition, because now because a volume can move up and down at the boundary, and so that is allowing system to take its own time in terms of the vertical side. So, now let us say if I create periodic boundary conditions and with the piston on top, now you can see there is also relaxation in the x and y direction. So, the blob has almost stopped moving downwards, because it is now going to take a random walk through the system, because it is now periodic boundary condition. So, now you can see that it is moving back and forth, and it is relaxed completely, confinement effects are gone. So, this is where it now becomes random walk, and again diffusion constant with the random walk with the Einstein's theories can be calculated using the mean square displacement, and you can apply the Green-Kuber formulation. So, this is a way that utilizing the simulation parameter simple potential model, you can take two phases of two different kinds of particles and see the diffusion of one into another. And with the temperature and pressure condition, you can also change models as they move forward. Thank you.